back to another video. Today we're going to be looking at a compound called Perthiocyanogen. Perthiocyanogen is a derivative of thiocyanogen, which is a very unstable compound. Perthiocyanogen is formed by the oxidation of potassium thiocyanate by either dilute nitric acid or chlorine. It's also possible to form it by the reaction of a potassium thiocyanate solution with nitrogen dioxide, but I haven't tested this fully quite yet. As you might know, or might not know, thiocyanates in the solid form react violently with nitric acid. If you haven't seen this before, let me give you a little taste of that here. So what I have in this dram vial here is some room temperature 70% nitric acid, and on this spatula I have some solid potassium thiocyanate. Now when I'm going to add this, it probably won't react at first. It's going to form a red solution, then it's really going to kick off at a moment's notice pretty much. So let me get a little bit closer and show you exactly what I'm talking about. Here's the nitric acid, and here's the thiocyanate. Yeah, now, just go in my shoes for a second. I tried preparing this a few days ago on a scale about 10 times this, inside.
Are you crazy?
You can already start to see how things went down then. So, a very violent reaction with lots of nitrogen dioxide and some sulfur dioxide produced. It's probably some potassium nitrate left in here with, nitrogen dioxide, carbon dioxide, and some sulfur dioxide produced as gases. Very violent reaction, but if tamed correctly, it will form perthiocyanogen. So, as I said earlier, this synthesis only really requires two things if you're going for the nitric acid route, which I hope you do because dealing with chlorine is pretty annoying, to be honest. You're going to need some water, you're also going to need some nitric acid, and some potassium thiocyanate. I think they meant to put thiocyanate, probably just a typo on their part. That's funny. Anyway, yeah, so just potassium thiocyanate, nitric acid, and water. Now, what I'm going to do first is dissolve this nitric acid over here in this water to create a more dilute solution. Now, honestly, I have absolutely no idea of what amounts to use because there are literally zero syntheses for this compound online, so I'm basically just winging it. That's how most of my chemistry goes, though, to be honest. Anyway, so what I'm going to do is add a stir bar to the water, and then dissolve the nitric acid with stirring.
Yay!
A few days later, and as you can see, we have a nice yield of absolutely nothing. Absolutely nothing. It doesn't fucking work. I don't know. Okay, whatever. Let's just move on to the chlorine route. Alright, now we're going to have to go the chlorine route, seeing as the nitric acid route didn't really work. This requires either very, very good ventilation, or for you to do it outside. Me, personally, I'm going to do this outside, because I don't really have a good ventilation setup at the moment. And, so yeah, in this beaker here, we just have some potassium thiocyanate with a stir bar, and I'm going to go ahead and dissolve this in some distilled water. The chlorine generator consists of a 1 liter 2-necked round bottom flask with a stopper at one end, which I will use to add the hydrochloric acid, a gas takeoff adapter with a rubber tube ending in a just a cut-off pipette, which will act as the outlet for the chlorine. And in here I have a slurry of TCCA, or trichloroisocyanuric acid, and water, just to help the reaction not slow down, I guess, because when you use dry TCCA and add hydrochloric acid, the reaction can get a bit sluggish and even foam over. So periodically I'm just going to remove this stopper and add some hydrochloric acid, then restopper it to resume the flow of chlorine. And we're literally just going to pass chlorine through a potassium thiocyanate solution, which will generate perthiocyanogen. It's that easy, really. So, with all that being said, let me go outside, and luckily for me it's actually pretty windy out, so that should blow the chlorine, or any chlorine that makes it through the thiocyanate solution, away from me. So, let's get to it. Now that I'm outside and have a decent source of ventilation, being the wind, I can go ahead and start the reaction. So in the larger beaker, sort of off to the left, I have some 50% by weight water and 50%, 31.45% hydrochloric acid, which makes about a 15% or so, maybe even a 15.5% solution of hydrochloric acid. I'm going to add this to the chlorine generator, which will then, begin to generate chlorine gas, which is going to be led through this tube and into this potassium thiocyanate solution. I'm probably not gonna... Oh, this wind. Yeah, that's exactly the reason why. I'm probably not going to have any, video audio during this, because it's just going to be that awful wind sound from the microphone. So I'm just going to go ahead and cut the sound from here on out, and I might come back, with any special updates or whatnot. So yeah, let's get started with this. As we can see, there is some perthiocyanogen crystallizing out or precipitating out of solution. This is the yellow color that you can see right now, and it's a good sign that our reaction is working. I found this reaction to be much more reliable than the nitric acid method of creating perthiocyanogen, just because, well, I mean, it works, and the nitric acid method really doesn't, in my experience. So, yeah, let's just keep going. There's still more perthiocyanogen to be had. Whoa, fuck. Shit. No, don't do this to me. Abandoned ship. Ah, fuck. I had to do it, but I dumped everything into the dilute hydrochloric acid. It was experiencing a runaway reaction. Son of a bitch, I've never experienced that before, so let me go ahead and dilute this with some more water to make sure I don't lose anything else. Okay, so here's the state of things after narrowly avoiding disaster. I salvaged the Perthiocyanogen and diluted it, the reaction mixture, which was, dumped in some 50% hydrochloric acid, with a lot more water, which seemed to prevent the reaction from going any faster. And knowing how the synthesis goes with nitric acid, I wasn't really willing to stick around and find out how that would end. So, what I'm going to do now is filter this. We've got a fair amount of nice precipitated Perthiocyanogen, if this thing would focus. You probably can't see it, but it's down there. And we're just going to filter this, and yeah, I'm going to stop the flow of chlorine, just add some more water to it, and just let that settle down on its own out here, and then we can observe the Perthiocyanogen. So yeah, let's go back inside. So, honestly, I have no idea what the hell's going on in this reaction. What I believe is happening, first is the formation excuse me, of perthiocyanic acid, which is generally a red color, as you saw earlier, which is then further oxidized by an oxidizing agent, a very powerful one. Yeah, so something interesting I've noticed is the difference between the perthiocyanogen formed from the sulfuric acid and nitric acid route, which I didn't show in this video because... No! I'm not doing that. And I'm just not going to show that. It was a bad synthesis. But this stuff is yellow. Sort of yellowish orange, almost like... I don't know how to describe it. Sort of like... whatever, but you get the point. So it's sort of a unique yellow color, and then the perthiocyanogen formed from the chlorine reaction is this nice, almost orange color. Actually, not almost orange, definitely orange, as you can see here. So there's quite a difference in color. Even though this one is dry, I do have some dry perthiocyanogen formed by the reaction of chlorine in a dram vial right over here. There it is. And that is here. You might not be able to see that very well, so let me get a little bit closer. There we go. This is perthiocyanogen formed by the reaction of chlorine with a thiocyanate solution. As you can see, it is pretty much the same color as that stuff down there, except this stuff is dry. It takes on a little bit darker of a color, but it's still perthiocyanogen as far as I know. At least I don't have any reason to doubt that it is. So here's the product. Some nice orange / yellow perthiocyanogen. Let's see some of the physical properties and see if it's soluble in anything. Now, the questions we must ask are, is it soluble in water? No. Methanol? Nope. Ethanol? I'm afraid not. Acetonitrile? That's a negative. Chloroform? Ethylene diamine? I mean, okay. Hydrozoic acid? Who made this list? Wait, no! But does it burn? They ask. Well, let's find out. There's something there. Ugh, smells like sulfur dioxide. I mean, not really, but nothing terrible. Here I have two oxidizers. On the right is sodium nitrite, and on the left is potassium perchlorate. I'm going to mix the perthiocyanogen with them separately, and then put them side by side to see how well they burn, if at all. Oh, that's weird. Some sort of static force or something like that. Don't. Alright, let's go outside and see how well these burn. Alright, so you might be able to see we're outside, and they're both on top of the soda cans, or at least overturned soda cans. So yeah, the nitrite mixture is on the right, while the perchlorate mixture is on the left. So I'm just going to go nitrite first, I guess. Oh, that's terrifying. It's not lighting up. Okay, so let's see how the perchlorate does, and let's also see if it kills me. Yeah, pretty nice, actually. So, yeah, pretty much what I expected. Perchlorates, at least in my experience, have been more capable oxidizers than nitrites in combustion reactions. So, yeah. Well, that's about all I have for this video. If you liked this video, you can like and or subscribe. Thank you very much for watching, and I'll see you guys next time. Special thanks to my Patreon supporters. Without you guys, videos like this would be impossible. Thank you.